So now this is something I want to minimize. So this is the result of a macroscopic analysis. Okay, and let's just pause a moment and contemplate on what we have here. What we have here is a natural minimization problem. It's a natural minimization problem of a function. Okay, so we can actually directly apply finite element to this problem, because let's actually go back to our last page and figure out if there is a similarity here. So on our last page, we want to approximate an arbitrary function, so we put some constraints, and we plug the constraint into this optimization problem, into the minimization problem. Here, the minimization problem in our last problem is the minimization between the approximating function and a target function, right? Now here, in this physical problem, I again obtain the minimization problem. And I can, if I'm able to use the same kind of a strategy to enforce a little bit of additional constraint on the function. So for example, what kind of constraint I can enforce? I can enforce the string to not be a string per se, but just a connection of two sticks. So basically, if I split the interval 0 to 1 into two elements, and I force the string to be a piecewise linear function, right? Just a connecting, basically I force it to be a piecewise linear function across the two segments. Then I can basically apply exactly the same strategy as I used in the previous page. I still have u0, u1, and u12 in this case, right? I have three variables to play with, and I'm going to be minimizing a slightly different objective function. But what you can find out is that I'm still going to get a quadratic minimization problem that'll still turn into three linear equations if I differentiate the objective function with respect to the three variables. I can still just solve these three linear equations for the three unknowns, and I obtain my solution to the differential equation. Well, in this case, actually, it's simpler. In this case, if I have two elements, because I already have boundary conditions, I mean, these two, the u0 and u1 are actually fixed, and I only have a u12 to play with. So I actually get a one-dimensional minimization problem. Of course, the approximation I'm going to get is actually going to be pretty bad if I just have two elements. So I can actually have four elements, right? I've split the interval into four elements, and then I actually have three things to play with. I have the value of u at a fourth, at a quarter. I have the value of u at half. I have the value of u at 3/4, right? So that way I get the three. I'm gonna have three unknowns. One objective function. I minimize the objective function with respect to the three unknowns. I get an approximating function. If I want more accuracy, I can split the interval into 1,000 elements, and I have 999 unknowns. I solve the same optimization problem. I get a much better approximation to the solution to this physical problem. All right, does it make sense? Any questions on what we went over for this physical problem here? Well, if you don't have questions, I have a question. How does this relate to differential equations? Okay, if you don't ask me, I'll ask you, right? So how does this relate to differential equations? We are trying to relate the finite elements to differential equations. So are we solving any differential equations here by looking at this physical problem? Well, we are. Okay, so let me tell you how this equation, this minimization problem, can easily be turned into a differential equation. Okay, the method we're going to be using is in physics and mathematics. It's called the method of variations, or the calculus of variations.